Okay, so let's talk for a minute about smog. Okay, we generally think about smog from industry and cars, basically soot and sulfur compounds that exist in water vapor. And smog is pretty much the most common air quality problem, and one of the ones that's somewhat difficult or a challenge to deal with. Okay, when we think about after World War II, all the industry and cars really created this what we call smog, or this brownish haze. Or photochemical smog out in Los Angeles from auto exhaust. Okay, so basically what happens is volatile organic compounds that we talked about earlier, these VOCs from the combustion of gasoline, are acted on by sunlight. Okay, and if it's cloudy, basically they get trapped. Okay, all of these VOCs get trapped on hot, sunny, and windless days. So when we think about, for example, the smog in Los Angeles, that's generally we think about certainly our smoggiest city in the country. It's very difficult for them because they are basically, if you've ever been to Los Angeles, obviously they're by the ocean, and then they're kind of sandwiched between the ocean and the mountain range that's there. And LA is flat at the base, basically, of that mountain range. And basically, if it's cloudy, the smog gets trapped there. The mountains kind of keep it there. If there is any wind coming off the ocean, it kind of traps, sandwiches it between the ocean and the mountains. And it's hot and sunny. And when it's sunny, basically those VOCs are acted on by that sunlight, okay, causing the smog. And if you've ever flown into Los Angeles in the daytime, you'll see that brownish haze that's just sitting over the city. It's really, I've never seen anything like that anywhere else, anywhere, okay, that I've been. So it's kind of a specific thing here in this country to Los Angeles. And yeah, well, it can lead to all kinds of breathing problems. People can have issues with asthma. Certainly we think of our young population and our seniors as being the most vulnerable. It can also impact trees and other vegetation, cause corrosion of metals. So it is a very serious thing that is, not good for ourselves or our environment. Okay, so on the over there, B, the B picture on your slide, the photochemical smog over Mexico City, that's kind of like what we would see in LA. It looks worse than it would probably look in Los Angeles. But yeah, so this brown haze has these nitrogen oxides. We think of the VOCs and that photochemical smog in those urban areas on hot, sunny, windless days just sits up there. And that's what it looks like. And then over on the left side, the Denora, Pennsylvania, back, half a century ago, okay, not even that long ago, our cities sometimes would look like that in the middle of the day, be completely dark, okay, because of poor air quality. So basically what happened in 1948 in Denora, PA, okay, like I wrote at the bottom of the slide, the air by the ground cooled overnight, and basically in the morning, usually the sun basically heats up the air, okay, we know that warm air rises, so basically the sun hits the earth, it warms the air by the ground, and that air goes up, okay, and dissipates, and everything's fine. But, when we had this smog event, the ground air was cooled overnight like normal, and the morning sun was blocked by the mountains, so it never got to warm up the air and disperse it upwards. Okay, we call this a thermal inversion, and it basically trapped that smog at the ground surface, and it killed 21 people, and thousands of people got sick from it. Okay, and this is kind of like when we talked about kind of the change over the 60s and the 70s into what we call, the modern environmental movement. It took, over 20 years after this, 30 years, okay, to get these regulations in place to kind of fix this problem. Okay, we had so much, industry, these different factories that were in these cities that were making this awful air pollution that was making us really sick. In 1952, 4 years after this, There was what we call London's killer smog, okay, where they had a similar event to the one in Denora, Pennsylvania, that killed a lot of people. So their killer smog. So, you know, we were both these industrialized countries that were certainly not kind of equipped to deal with all this pollution we were putting up into the atmosphere. And certainly a couple decades later, we put in regulations to protect ourselves from never having to have those types of experiences again. On this slide, you'll see look at the formation of photochemical smog. When we think about our cities, whether it's Los Angeles or Mexico City, we often see this brown haze, which is this photochemical smog that forms from a series of chemical reactions in the troposphere. So we see that when the sun hits this, basically it splits that nitrogen dioxide into an oxygen and a nitric oxide, NO, and then that oxygen atom can combine with O2, or the oxygen that we think of, that we breathe. It can combine with that, forming tropospheric ozone. And we'll talk more about tropospheric ozone a little bit later as a major air pollutant, in the concern that we have related to tropospheric ozone in the air that we breathe. It can cause serious health concerns for people in these cities that have high ozone days in the summer specifically, where ozone builds up and can cause breathing problems for people with respiratory issues and asthma, etc. And that, you know, can also be caused by the buildup of VOCs, which are volatile organic compounds that are primary pollutants, forming that secondary pollutant that is the ozone through those reactions in the troposphere. So a really big concern, certainly in Los Angeles and Mexico City. You'll read in your textbook related to the Sister Cities program, and how that basically what they have in common, and why they both have this issue related to photochemical smog. All right, so when we think about all of these different types of air pollutants, we think about smog. There's a lot of different effects that air pollutants can have on us in our environment. About 4 million tons of hazardous air pollutants are released in the United States each year. Okay, that's a lot, and we always kind of think of it as just kind of going up and going in the atmosphere and not causing any kind of problem. But a lot of things stay in our troposphere and can have impacts on our health. Okay, often it's hard to determine what the cause is, like if you're having some kind of respiratory problem. Is it some kind of respiratory infection? Do you have asthma? Do you have, are you allergic to some kind of air pollutant? Okay, that is a hard thing to figure out. What is really triggering symptoms that you might be having? It is very difficult. And usually it's some kind of combination of different types of pollutants, different things that are irritating your respiratory system. When we think about, our physiology, okay, we don't, we have our mouths and we have our nose, okay, we don't have a lot of openings to the outside world, and our organs are not really exposed. We're protected by our skin, okay, to basically keep things from negatively impacting our organs. But when we think about our lungs, they are really exposed because, what we inhale, okay, goes into our lungs. And whatever's out there, if we don't have some kind of barrier between that, it's going to go into our lungs. Okay, we have, we like to breathe in through our nose because we have some protection there. We have mucus, we have hairs, okay, and they trap a lot of dust and particulates and things that we don't want to go into our lungs. Okay, but, it's not good enough, protection from things like asbestos and, these other air toxins. Okay, it doesn't keep them out. Okay, we have to wear specific, protection to keep our lungs healthy. Okay, because they are really vulnerable. They're very delicate tissue, and they can easily be negatively impacted by what we inhale. Okay, so we usually say the effects can come in 3 different categories. We can say that it's some kind of chronic effect, which is basically a gradual deterioration of function over time. You could have chronic bronchitis or scarring of your lung tissue. Another chronic effect would be asthma, for example. That would be kind of a chronic respiratory problem you might have. Maybe heart disease, okay, over time, again, can impact your breathing, immune system problems. These are things that are kind of constant, fluctuating on and off, but kind of lifetime, generally lifetime issues, okay, chronic exposure or chronic impact. And when we think about acute, okay, that's a little bit different, okay. We're thinking about, this type of pollutant bringing on some kind of life-threatening reaction, okay, and could be a relatively short period of time. Okay, so you might have a chronic problem like asthma that you might manage and live with just fine for your whole life. But then one day you come in, in contact with some kind of a trigger for your asthma, and you have some kind of acute response that you need your rescue inhaler, okay, for. So we say that's an acute, basically, when some kind of pollutant brings on a life-threatening reaction in a period of hours, minutes, seconds, or days, like a shorter period of time. Okay, usually when people have an acute reaction, it's because they already have some kind of chronic issue, some kind of ongoing issue that is triggered. Usually they're suffering from some problem that they already have, and it's been aggravated. Okay, so if you have some kind of emphysema or some kind of issue with your lung tissue, and then you're exposed to ozone, for example, it could absolutely aggravate it and could be potentially life-threatening. Okay, the last category there is carcinogenic, and like I mentioned earlier, carcinogenic means that it's cancer-causing. So basically, when we think about for example, radon, we said that's radioactive gas, and therefore releases radiation that can cause cancer. And basically what happens is this radiation changes your cells. It can mutate them, okay, causing there to be that uncontrolled cell growth that is cancer, that can cause a tumor, etc. So very serious, and we certainly do not want to be overexposed to anything that is carcinogenic. Okay, other effects besides us occur on agriculture and forests, and we're going to kind of talk about more of that on our next slide when we talk about acid deposition. But when we think about, for example, sulfur dioxide, that leads to acid deposition. It can deteriorate trees and vegetation, downwind of power plants. Okay, so basically we're kind of gassing these organisms that are out there that, again, can be impacted. Okay, we think about our plants. Okay, again, they should have access to clean, healthy air as well. All right, so we think about acid deposition, changing the pH of the soil from acid input. That can impact how trees and vegetation function and grow, etc. Okay, I remember years ago I took my cat to the vet, and there was a little Siamese cat there that was sneezing, and the cat was there for the cat's allergy shot. And I thought, well, that's kind of interesting. I guess, the cat has some kind of allergy as well, some kind of airborne allergy. And so it's not just us, we're not the only ones with lung tissue. Other organisms are going to be sensitive to different things in the air as well. Okay, I want to specifically narrow in on what we call acid deposition. And we call it acid deposition because it can really come from all different types of it can come down in the form of many different forms, whether it's rain or snow or sleet, acid fog. Okay, any way that water is going to be redeposited on Earth, acid can come down with it. Okay, if it's up in the atmosphere. Okay, and keep in mind that acid deposition, sometimes it's hard to figure out what the source of it is. because remember, with our air patterns, certainly pollutants go up into the air, but they don't get redeposited right exactly there. They're going to go up and they're going to move with the wind, etc., and they can be deposited thousands and thousands of miles away from where they were emitted. So, we know what goes up must come down at some point, but when it goes up, where it comes down is a whole nother question. Okay, so what is it? Okay, we think about the pH, okay, of our normal rainfall being actually pretty acidic at 5.6. Okay, we know that neutral is 7, and anything below 7 is acidic. Anything above a 7 is basic. So the pH of normal rainfall is 5.6, which is slightly acidic, right? Or kind of, relatively acidic. It's not neutral, okay, like we think about our tap water or most of the water in our bodies. All right, so we define acid rain or acid deposition at basically anything 5.5 or lower, and usually acid rain is about 4.5. Okay, so a whole number lower. And remember that when we talk about acids and bases, and we think about the pH scale, okay, it's a logarithmic scale, so it's not going to be, just a little bit more acidic. Every step you take on the pH scale is 10 times more acidic or basic. So, for example, if we're going from, rainfall that's 5.5 on the pH scale to 4.5, 4.5 is actually 10 times more acidic than 5.5. It's not just one, a little more acidic. It's 10 times more acidic. And if it comes down at 3.5, that would be 100 times more acidic than 5.5. So it's really magnified as you move away from neutral. Okay, when we talked about air pollutants, we talked about the fact that sulfur oxides and nitrogen oxides can contribute to acid deposition. For example, H2SO4 is sulfuric acid that can form in the atmosphere when sulfur oxides are put up there. And nitric acid, which is HNO3, as well can form up in the atmosphere when nitrogen oxides are emitted. Okay, we think about different types of fossil fuels being burned. We talked about sulfur oxides coming from coal burning. And basically these acids will dissolve in water and then again deposit themselves back on Earth. All right, as we describe all this, fossil fuel burning, that's what we call as anthropogenic or human-caused air pollutants. Okay, it's estimated that we pump up into the atmosphere or emit between 100 and 130 million tons of sulfur dioxide from coal burning every year. And that is the area that certainly the EPA has been trying to decrease, and one of the big concerns about coal burning. Okay, also mercury being emitted as well from our coal-fired power plants. So when you hear coal's on the decline and we're trying to crack down and make cleaner coal-burning coal-fired power plants, that's what we're talking about. Really cleaning that, cleaning those air pollutants out of there. Okay. In addition, we release about 60 to 70 million tons of nitrogen oxides a year, and again, these are concerns because again, there's multiple facets of the harm that they cause. But earlier there, number one, I put that it can be naturally caused as well. Things that are natural like volcanoes, sea spray, certainly microbes. Okay, anaerobic bacteria release sulfur oxides. Okay, if biomass is burning, like our natural forest fires, lightning, they can release nitrogen oxides, okay, into the atmosphere. So these things are naturally occurring, but we're just putting a lot more of them up because we're burning a lot of organic matter, okay, way more than would naturally occur. Since the regulations related to the Clean Air Act, we have seen improvements in precipitation here in the United States. Precipitation has become less acidic, meaning that the pH has actually risen. So we don't see our precipitation as being nearly as acidic as it was prior to the regulations from the Clean Air Act. So you'll see there back in 1990, obviously our Clean Air Act was in the 70s, but we see that we have less acidic rainfall. Okay, I mentioned that, you know, acid rain, we think of you know, below that 5.5, 5.4 level. We used to see areas, certainly in the East Coast, where the wind generally comes from, you know, west to east, generally comes from south to north, that the East Coast, especially the Northeast, generally gets a lot of this acidic rainfall because of the movement of air pollutants across the country from the Midwest, from the west, to those northeastern states. And again, we see that pH very low, more acidic, you know, 25 years ago, and now here we see today that pH has actually come up, meaning that the rainfall is more basic, more normal, and that's really due to less sulfur dioxide, the cap-and-trade system regulating those pollutants getting up into the air and then redepositing themselves in our states as a result. Okay, so what are the effects of this acid deposition? I would say that, you know, we have the least amount of direct negative impacts of acid deposition. But because it affects our environment, our aquatic system, our forests, it can obviously negatively impact us more in an indirect way, okay, kind of on a second level there, where it might affect our forests and then we don't have that resource. It might affect our aquatic systems. We might not have the fish that we want to eat. So I'm going to start down with humans, and then I'm going to go backwards and talk a little bit about aquatic ecosystems and forests. So when we think about humans, like I said, it doesn't affect us really directly. It's not like we're going to burn our skin because acid rain is going to come down and burn holes in our skin. It's not going to affect our health directly. But it can do damage to things that we like. Okay, for example, it can deteriorate our artifacts, limestone, marble monuments. Obviously, we know acids can erode, either corrosive. Okay, so they can cause basic corrosive damage to buildings, etc. And from a human standpoint, I would say it's generally more of a economical impact. Okay, because it's expensive for us to have to fix these problems if we have, for example, corroding construction, for example. Okay, but in terms of a direct impact on our bodies, there is not really a direct impact. When we talk about our aquatic systems, there is a significant impact on them. It causes a lot of stress. We know that certainly a limiting factor for our aquatic species is the pH of the water. And when we're talking about acid input, that can seriously drop the pH of the water and cause a lot of stress for a lot of species that live there. Okay, for example, in fish, it can affect their enzymes, how the enzymes work. It can denature their proteins, which, again, enzymes are a type of protein. So it can denature them and cause them to basically get misshapen, and then they don't work right. They don't make the body work right. Okay, so enzymes, proteins, hormones, it can really have a negative impact on young fish and eggs, which are particularly sensitive. Acids can cause aluminum and other heavy metals like mercury to leach from soil. Okay, when it leaches from soil, it can dissolve in water and then be absorbed by organisms' tissues. And we know that aluminum and other heavy metals like mercury, cadmium, lead are bioaccumulators. So we said that, you know, basically if the acids cling on to metals that are kind of stationary and they run off into our water systems, they can accumulate in our aquatic systems and then magnify, etc. And that can be certainly an impact not only on our species there, but that could be, you know, an effect on us down the line. Sometimes you can't eat those fish if they are contaminated, or sea life. And basically our lakes and our ponds and our aquatic systems, if we took the pH of our aquatic systems, we would find that they have a higher than neutral pH. Generally, we like to see a pH of about 8 in our systems. And you might think, oh, I would thought it was 7. Okay, nice and neutral, but it's not. Okay, natural systems out there generally have a pH of 8. They're slightly basic because remember, normal rainfall is acidic. It's like 5.5. So basically, when the acid hits the base, those neutralize each other. And we basically call that the buffering capacity of the water. It has a good buffering capacity. It can buffer against that acid coming into it. And it can do that because there's something called bicarbonate in the water. Okay, and they can deal with that. But what happens is, even if, water is slightly acidic, okay, like acid rain, comes in, well, it's possible that a body of water can buffer against it because it's got a pH of 8. Okay, so it can kind of neutralize some of that acid that comes in. The more that comes in, the harder it's going to be for that body of water to neutralize it. So when we think about, for example, a big massive amount of snow, so if we have a lot of snow, or I should say acid snow, and it's sitting there for months on end, and then all of a sudden we have a spring thaw and all that snow melts, that acid snow melts and goes into waterways, it can do what's called acid shock, that body of water, where it has a huge acid input all at once. And it can flip a body of water and make it go acidic and just kill all kinds of organisms in there. And we see acidified lakes. We see acidified ponds in Pennsylvania, in New York State. Okay, the Midwestern emissions that we emit up into the air are often redeposited in New York State and Pennsylvania. That's where that rain falls. Okay, it goes up here and it goes down there. And they have a lot of acidified lakes there. And again, those are areas that build up a lot of snow and then have massive melting and massive inputs of acid. Okay, the last category that I want to talk about is forests. And we noticed that back in the 1980s that our forests were declining. Okay, certainly these ones that we saw out in the Adirondacks in New York and Pennsylvania, basically plants basically becoming really vulnerable and weakened. They'd lose their needles and leaves. They'd be more susceptible to insects and diseases. And we'd see a lot of the nutrients that they need being leached from the soil by these acids. Okay, and you might think like there was a forest fire somewhere, but it's actually just an acidified forest. And without the nutrients, it can also be, for example, like lesions on leaves because they're actually getting burnt. The leaves are getting burnt by the acid deposition. So it can really weaken their immunity, okay, to fighting off insects and diseases, etc. And we can see forest decline as a result. Okay, so here's a slide of some of the impacts, some of them I mentioned, of acid deposition. And you'll see there the leaching of certain cations. You'll see calcium, magnesium, sodium, potassium, which counteract acid deposition. So they basically leach these kind of elements or ions that have the ability to counteract the impacts. So when they're removed, they can't basically neutralize that acid. Okay, so you see the extra sulfur and nitrogen accumulating in the soil that can over-fertilize. We talked about concerns about over-fertilization in areas where it shouldn't be. Dissolved inorganic aluminum, okay, can impact plant uptake of their nutrients that they need. Calcium being leached from needles and causing issues with them dying from their freezing in the winter. Also, the sugar maples being impacted. Sugar maples are really sensitive, and when we leach their cations from the soil in their leaves, it causes them to die. And again, they're really sensitive, so there's a lot of things that are negatively impacting them these days. You'll see those Adirondack, the New York, New England lakes I mentioned, that there's a high percentage of them being acidified, so they can't certainly contain the same kind of organisms that they used to. And that lowers the lake's capacity to neutralize further acid, so it doesn't have that buffering capacity. They're too acidic already. Okay, it needs to be basic to be able to neutralize the acid input. Elevated aluminum levels, and obviously all of these things reduce the species diversity or biodiversity that's out there. And that affects food webs. We don't like to see our ecosystems decline. We talked about at the beginning of the semester our big concerns, two of them, are ecosystem decline, and that loss of biodiversity. And those two things go hand in hand. And things like acid deposition contribute to that.